Hello everyone. The purpose of today's lab exercise is to use an optimizer to obtain the best possible tuning parameters for a PI and a PID controller. And we are going to be using fmincon, which is a nonlinear programming module in MATLAB, to minimize what I am referring to as the integral absolute error, but I think we may have to change the objective function. For the closed loop regulator response, we are going to repeat the exercise for the closed loop servo response. So what we want to do is minimize, let's say we got a PID controller. PID controller has unknown tuning parameters Kc, tau I and tau D. So we want to minimize over Kc, tau I and tau D as our decision variables, an objective function J, and what I have said here is J is equal to integral absolute error. Integral absolute error is actually defined as integral of, from, let's say the system is initially at rest, from time t equal to 0 to infinity, or whatever is t final until the final simulation time, absolute value of the process variable minus the final value of the process variable at which it settles dt. This is called the integral absolute error. There is also what is called the ITAE, integral time absolute error. And what integral time absolute error does is you just multiply it by time. This is what integrated time absolute error is. I did do the exercise, played with the numbers a bit, and figured out that both these objective functions result in tunings that are too aggressive for the regulator response. So what we will use, in fact, we will use any of these J's and see how the optimizer changes. Integrated square time absolute error. So this is equal to integral of t square times absolute error. So you can see ITAE is penalizing deviations after long time more because you're multiplying by t. T square is more severely penalizing deviations as time progresses. So if initially y is away from y final, that is not penalized as much, but if y is away from y final at long times, that is penalized much. Yeah, so these are just sample objective functions. You also have the ISE, integrated squared error, which actually is integral of y minus y final whole square dt. This will give extremely aggressive tuning. So whichever of these objective functions gives us reasonable responses, that is what we will use. So I hope the exercise is clear. We want to use an optimizer to obtain the optimum tuning parameters Kc, tau I, tau D for a PID controller. We'll also repeat it for a PI controller. I think just using P or integral only controller, let that be, because when you want the process variable to end up at set point, integral action will always be there and proportional action should be there for speed of response, and we want tight control. That is why we are optimizing. So using P or I control doesn't make sense when you want tight control with no offset. So we will just limit ourselves to PI and PID. So that's the exercise that we are going to go through. With that, let's call it quits and go to our simulation environment with that brief overview. So I'm going to say quits here. Don't save. Let it go. This was the problem description in a Word file. So now let's go to MATLAB. And this is the file that we built yesterday or in Lab 1. And we've got a PID controller. And if you double click on the PID controller, you can choose reverse action, direct action, and you got controller gain, integral time, derivative time. Okay. Now, if you do fmincon is the optimizer that we have available in MATLAB. So go to the MATLAB window and just type help. Just type help fmincon. And you can read through it, but basically what it does is if I look at these inputs, what are these inputs? Fmincon, minimize the objective function 3 times sine x of input 1 plus exponential of x of input 2. So that's your objective function. This is your objective function. This is the initial guess. It's a 2-variable problem. And then there are other things that you say, equality constraints, inequality constraints, lower bound, upper bound, etc., etc. As I use it, it will become clear. Let's see. Okay, so here it is. So fmincon of a function with an initial guess. Fmincon of a function with an initial guess. Equality constraints ax equal to b, or inequality constraints, I don't know. Let's see. Okay, if you see this description, understanding what is important. Let's see. It minimizes the function fun subject to the linear equalities a equality times x is equal to b equality. So these are equality constraints, as well as a times x is less than or equal to b. You must set these to empty if there are no inequalities. And similarly, a and b are to be set to empty if there are no equality constraints. You also have this lower bound and upper bound on your decision variables. And then you could also have nonlinear constraints. We have no nonlinear constraints. And you could also give some options that set parameters for the optimizer. Okay. So this is the form that we are going to use for the optimization. And I also wanted to tell you something about sim. Help sim. Help sim runs a Simulink file as a command. Wow. So you just man. So you just run. Let's see. Lots of stuff, but the sim simulates your Simulink model where parameters represents a list of parameter values. Blah blah blah. We're not going to do anything. We're just going to simulate our room model.slx. Yeah, so that's all we're going to do. So let's say what we want is simulate for a. So let's say what we want is minimize the integrated absolute error for the regulator response. Regulator response is a 5 degree Celsius change in the ambient temperature. Okay, so let's just say this is what we want to minimize the integrated absolute error for, with Kc. Hang on. Kc is not declared in the parent workspace. We'll declare Kc Ti. That's why it's gone red, and Td as the what happened here, and Td as my controller tuning parameters. So I'll go into my main workspace and say that okay, let's say Kc is equal to 10, Ti is equal to 10, and Td is equal to 2. And now if you run your simulation, I think it should run. We will just apply it. ये क्या हुआ यार? Okay, let's see what happened here. Yeah, so now there is no redness there. So what that means is Kc, Ti, and Td exist in the parent workspace. And now if you just run the simulation, you will see the kind of response that you get. And since we started it after such a long time, the first simulation will take time to run. Okay, so this is what the response looks like. 25 degrees Celsius, you go up because the ambient temperature is increasing, the room heats up, and then this temperature goes back, and the controller brings it back, and by about 60 minutes the response is over. That's a very nice smooth looking regulator response. Deviation is 0.8 degrees Celsius, maximum deviation is 0.8 degrees Celsius, and we can see what the response looks like. Now let us say I want to adjust Kc, tau I, and tau d so that the integrated absolute error of this response, what is the final value? Final value is 25 degrees Celsius. Final value is the same as the initial value. So integral of y minus y final, which is 25 degrees Celsius, absolute value of that dt from 0 to, I would say, 100 minutes, that integral is what is integrated absolute error. Okay, so this is what we want to minimize. So let us make a function, and I already made a function, so I'll just walk you through it. This IAE. Yeah, so if I open this, kholo bhaiya, okay. So what you have is j is equal to IAE. X is the variable that contains Kc, tau I, and tau d. File name contains the name of the file or the model that we want to implement. Kc is the first input, Ti is the second input, Td is the third input. With these values of Kc, and these are declared as global, so they are available to the main workspace, and because they are available to the main workspace, they are also available to your model. So model will simulate the PID controlled response with these guessed values of Kc. So sim will simulate this model, and then j is okay. So here I have used ISTAE. Let's just do it for IAE and see what kind of an optimum we get. Okay. So let me save it. And I'm thinking we don't have to simulate for so long. So maybe we should simulate it only for maybe half the time. Simulate it for only half the time. Run it so that it's written in the executable file, and so that file executable is what gets executed by sim. All right, so we go back to the MATLAB command window and then say okay, my decision variable, which is x, and my objective function, which is j, is going to be equal to, and what is the file name? Room model. I did it previously using, but we'll just use room model because that's what we developed. This is my file that I want to simulate, and my final value because this is the final value that needs to be given. If you see here, you have to give the final value and then it does minus. So my final value is the same as the initial value, 25 degrees Celsius. So I've just put in TIC here. By the way, TIC, WIC, and those variables exist in the, see, TIC is 25 degrees Celsius over here. So these exist in the main workspace. I'm just taking it from where we left yesterday or in lab 1. We are saying that the initial guess for KC, TI, and TD are this. There are no inequality constraints, so A and B are empty matrices. There are no equality constraints, so A equal and B equal are empty matrices. Lower bound is this for KCTI and TD in that order. Higher bound is this for KCTI and TD in that order. There are no nonlinear constraints, and there's something in the options that I've done. Maybe I should show that also to you. So just do Control C. I'll show you the options bit later on. Let's one. Okay, so options is not recognized. So okay, fine. So we'll so options is Control C. Options is equal to optim set for what are the default options for fmincon. These are the default options for fmincon, and let's just see. And you can see what these default options are. I'll just, so that we have some more space, we can see some more stuff. So you can see what all we have here. The algorithm that we're going to use is interior point. There's also trust region, and I think there's also SQP, and then there's also active set method. Tolerance of the function 1e negative 6. Maybe we can relax this a bit. Doesn't really matter. Display, you just display the final result. I think I want to see the results as I want to see results as things are iterating, and guess for the decision variable is being updated. So we'll say options dot display is equal to iter display and now let's run that command again and see how things shape up. ये क्या हुआ है? Oh, I think global, they are not global. Global KC TI TD comma Y. These need to be declared as global. Let's see. Run it again and see if it runs. Yeah. So last time it did not run because KC, TI, and TD were not global, so their values were not changing, and therefore there was no change in the objective function, and therefore the optimizer exited. Now that KC, TI, and TD are global, the changes that the optimizer makes to KC, TI, and TD go to what? Go to room model, and with those changed KCTI and TD, the simulation runs, you get the response, you calculate the J, which is integrated absolute error. And so these integrations are proceeding, these iterations are proceeding. Let's see. When will it exit, my friend? This must come to -7. Norm of the step must become small enough. Yeah, I think it should be out very soon. Yeah, there we go. So stopping criteria has been met. So let's just see what X is. X is so KC is 25.57. Integral time tau I is 4.1262, and TD is 2.57 approximately. How does the response look? Close all, plot. Let's just see how the response looks for number 2 is temperature. So let's see. There we are. It's rippling, but you can see the rise is very small. Earlier it was going to 25.8 and then reducing by 40 minutes. See, the response completion there was about 60 minutes. Here I have come to within zero point 0.1 degrees Celsius in 10 minutes. But this oscillatoriness is a cause for concern. And one way is to suppress the oscillations at later time is to penalize them more, and one way to do that is take ITAE instead of IAE. So I will go to my IAE file and यहाँ पर जो है I will say star y all comma 1 star नहीं dot star sorry dot star element by element multiplication y all comma 1. By the way, this point 1 is the delta t. So we are just using rectangular integration, and the difference between one time step and the next time step is zero point 0.1. How did I set it? How was it set? If you go to room model, is it open? Let's see. Yeah, room model is open. So if you look at this guy and if you go to modeling and if you go to model settings, you will see this. So I'm using a fixed fundamental step size of 0.1, a fixed step integrator. There's all kinds of options, numerical integrators. I'm using ODE2 with a step size of 0.1. Okay, so that's why in the numerical integration delta t is 0.1. Yeah. So getting back to IAE, now I multiply it with time element by element, so I get ITAE. Save this guy. Let's run the optimizer again. Now that it has been saved, let's run the optimizer again. Chala do. So it's running. And you can see objective function is decreasing and then it'll stop decreasing and ultimately it'll get out. I'm sorry we have to wait like this, but no option other than to wait it out. Maybe I can make my tolerance a bit less and then it'll come out earlier. Yeah, it should be coming out now anytime. 9. There we go. So after 48 iterations, we are able to zone in to our optimum and oh shucks, no, sorry. X, let's look at X. Less aggressive, integral time is a little more, but I don't foresee. Hold on. Plot. Let's make it magenta and see how that plot looks like. So magenta is slightly looser, somewhat looser, uh, and smoother also, not as oscillatory. Let's try IT square absolute error. So I'll go back to my IAE objective function and say, okay, instead of multiplying by time, let me multiply by square of time. So dot exp element by element exponential or to the power 2. So square of time. Save it. Let's run it again. Let's see. चला दो भाई. So now again it will take a couple of minutes to converge. So we'll just have to wait those couple of minutes. Takes longer. Yeah, it should be coming out anytime. There we go. So let's look at our tuning parameters. So the gain has reduced. The integral time has also increased a bit. Tau d is somewhat lesser. Let's see how the response looks like. We'll plot this as a black curve. See that? See it? Yeah, I like the black curve the best. Control is tight and it's much smoother. So I suppose we will use these tunings. So the objective function had to be adjusted a bit because the blue curve is too oscillatory. That means it's too close to instability. The black curve seems reasonable. But now let us run for this tuning. So if you look at KC, KC is this. If you look at TD, TD is this. If you look at TI, TI is this. So for this tuning, let's get the what kind of response? Let's get the servo response where the set point increases by 1 degree Celsius and there is no disturbance. So we will say that this guy is actually 0. Apply. Okay, just press play, simulate it, and maybe I can just see it over here. See now, you go from 25 to 26, but then you get a very large overshoot from 26 to 26.7. So the change in temperature is 1 degree Celsius, but the swing is 1.7. So you get a 70% overshoot. I mean, that is to be expected because we tuned for the best possible regulator response. We optimized the regulator response ISTAE. Now we'll say, okay, in most situations, in chemical processing situations, usually it is the regulator response that is more important. Set points are seldom changed. For example, run the reactor at such and such a temperature because this is the best temperature for the catalyst that is recommended by the supplier of that catalyst. Or the tray temperature of a distillation column should be so much because at this temperature you get the right separation, and so on and so forth. So the set points of temperature controllers are usually fixed, and what the controller is supposed to do is handle changes in load or in disturbances. On the other hand, in aerospace systems, for example, set point tracking, or in robots, set point tracking is more important. So it all depends on the application whether servo response is more important or regulator response is more important. If servo response is more important, then we'll optimize the servo response integrated absolute error. And so we can do the same thing. So let me do the same thing. Maybe I should maybe I should write down these numbers. Regulator response numbers was Kc is equal to 25.6 approximately is fine. Tau d is tau I कितना है? Tau I is equal to 5.86 and tau D is equal to 1.72. So that's the optimized regulators controller settings. Now let me optimize the what shall we say, the regulator, the servo response. Okay, so let's see. In this case, the final value is TIC plus 1 and everything else remains the same. Just press play. Chala do. And we are optimizing integrated square time absolute error. That's what we are optimizing or minimizing. Let's see where it goes. So we'll have to wait it out. So maybe a couple of minutes till the optimization gets done. It'll take about 50 iterations. More than 50, yeah. Okay, 52 iterations, and let's see what the this is what the optimum settings look like, and maybe I should have another figure and plot. Yeah. Okay. ये क्या हुआ है? This doesn't look right. ये तो गड़बड़ लग रही है भाई. I think, yeah, I really think, यार ये तो सही है. ये भी सही है. अच्छा कोई बात नहीं. तो इसमें ITAE is not giving such a good result. So it all depends. The objective will also have to be adjusted. Okay, so let's see. Let me just do an integrated absolute error and see what kind of result we get for that. इसमें जो है इसको हटा दो. No time business. This is just clean integrated absolute error. Yeah, so let's run it again. Final value is TIC plus 1. Yeah, that is true. Chalo, we'll see what happens. Sorry it's taking so long. But सब्र का फल मीठा होता है. That's what they say. Okay, so that's that. Okay, next. This is what I was expecting. This is what it should have been. ITA. So now if I plot, This is for integrated absolute error, so this should be blue. Let's see. Oh man, look at that. Pretty damn good, huh? Okay. Let's see if I do IAE. ठीक है ITAE करते हैं. Now let us optimize for a PI controller, no derivative action. So in that case, what I will have to do is, I'm sorry, this is somewhat ad hoc. We will not optimize this guy. Yeah, so we'll just change x1, x2, and let me say TD is equal to 0 globally. So TD is 0, and now we can run this. There should be no problem. Yeah, so when we run it, we got to make sure that the third option is removed. So the third variable, which was corresponding to TD, is removed. So this is removed, and even in the initial guesses, it should be removed. So this is also removed. Let's optimize. So now we are optimizing for a PI controller. Then again, we'll have to wait it out. Actually, we're just hovering around the optimum. Okay, this is what it looks like. If I plot no derivative action, I'll call it red. Let's see. Hold on कर लेते हैं. Otherwise, it will overwrite and we will not be able to compare. So hold on and plot. Let's look at the picture. There we go. You see, PID control is the blue curve. Red curve is PI control optimized. We minimize the integrated absolute error, and you can see PID control is much faster, but PI control is not bad either. It is looser though. So the best PID control is much tighter compared to the best PI control, and you can repeat this for the regulator response, and hopefully you'll see the same thing. And I encourage you to do these things. Compare IAE, ITAE, ISTAE responses. In your responses, also plot the manipulated variable, the controller output, the implemented output kinds of responses, and make some very neat plots of the kind that I showed you in the last lab, and submit a short report of no more than 2 pages summarizing your results. What was your tuning that you got that was optimized, and what kind of objective function makes sense for set point tracking, what kind of objective function makes sense for regulator response, and that will be that. With this, we come to the end of this brief tutorial that explains or walks you through whatever you're expected to do in lab number 2. Thank you and goodbye. Hope to see you next time. Good day.